record it. And we can get started with our review. So hopefully you guys brought lots of questions you want to see worked out, problem solved, ideas to discuss. Remind you that there's that review packet for the final exam. So, oh, actually, I've already got it open here. So if you don't have it yet, I would suggest taking a look at this thing. I'm going to paste into the chat the link and the review. Alrighty, and I'm going to switch over to the dot cam. And we should be good to get rolling. On the final like project 3. I would say yes. So Dan asked, are there going to be problems of the same sort of difficulty level as we're on project 3 on the final exam? The project problems are the same sort of thing that we can ask you about on the final, but they usually involve many parts and they go on for a while. So you can explore a concept a little bit more deeply. And the questions on the test are going to be about the difficulty of the individual things that you had to do on that project. But I wouldn't expect, you know, something like on project 3, the third question had 3 parts or 4 parts, right? Where you had to calculate the amount of interest that was earned on each of the different accounts, like the one that was better. Any one of those parts would be about the length or difficulty of a final exam problem. So yes, there will be problems about that hard, just not that long. So bot cam booted up. Oh, no, not the integrated camera. Where are you, bot cam? Why aren't you showing up here? Hey, Nova. Sorry, one of my cats is an asshole, apparently. There we go. All right. So I'll share that with you guys, and we can get going. What would we like to do? It is your day. We got 2 hours. So whatever you guys would like to do. And I can just start pulling problems out of that review final thing I pasted in chat if you want. But I'll do stuff that you guys are stuck on. I'd rather do things that are specifically useful to you. So what do we want to see? You can type in chat or I'll just shout whatever you want. Do that. I'm going to go ahead and have an instance of MML popped up that's got your classes open. So were there any specific requests there? Any particular problems you guys wanted to do? Could come from the homework, quizzes, any of the tests, projects, activities, any of that stuff. Or of course that review packet. If not, then I'm just going to start plowing from the review. Yeah, okay, good. 47 from the review. That's so the 47th problem in that review packet asks us to expand each of these logarithms. The first one is a natural log, and inside is a square root of 4 times xy. So let's get started on this guy. If I want to expand that log as far as possible, what would be a good place to get started? Mesa asked if we could do something to do with rational functions. Sure. So the way I would get started on this guy is by rewriting the inside of this logarithm as a power, because we have a rule that tells us powers inside logarithms can come down as constant multiples out front. So 4xy under a square root is the same as 4xy raised to the 1/2 power. And then that 1/2, you can come down front as a multiple. So you get 1/2 times the natural log of 4xy. We're using there. This one. And then from here, inside the natural log right now, I really have two products, right? I have two instances of multiplication there. And I can split those up using the rule that says multiplication inside of a logarithm is the same as addition outside the logarithm. The 1/2 is going to come along for the ride. So I'll write a 1/2 and then open up a big bracket or parentheses. And then the natural log of 4 times x times y is the natural log of 4 plus the natural log. If I wanted to really break it down into steps, I could say I'm going to write it as ln of 4 plus ln of x times y. But I know that the ln of x times y is going to get split up again in the same way. So if I split it all the way up, and I know this is what we're always tempted to do, is to do all these things at once. This is one of the few cases where I would say maybe that's not a bad idea, because it really is clear what we're doing. But we use that rule that says that the log, regardless of the base, with multiplication inside, is the same as the sum of two logs, with that same base a there, base a here, added up on the outside. Right. So here we use this rule, here we use this rule, and then I would distribute the 1/2. So this is 1/2 times the natural log of 4 plus 1/2 times the natural log of x plus 1/2 times the natural log of y. Everything that at the start had the 1/2 power should have a 1/2 out front. And since everything was under the square root, everybody's going to end up with the 1/2. So that's the first part. Any questions on the first part? Okay, John wants to look at one of the project problems after this. So we'll do a rational function and then a problem from the project. Part B is asking us to expand the natural log of, and I'm not sure if I'm reading that right, as a cube root, square root, cube root of 2x over 4. So that's the cube root of 2x all over 4. The 4 is not in the root, but the 2x is. So same problem, packet 47. We want to expand this guy. I have a rule that says division inside a logarithm is the same as subtraction outside, just like this multiplication is the same as addition outside. So I start by writing this as the natural log of the top minus the natural log of the bottom. All right, here I'm using, I'll try to squeeze this last rule in. This says a log with division inside is the same as the difference of logs with the same base subtracted outside. So these are the rules. And here we use this rule. Next, this piece is a lot like this piece, right? A lot like the square root piece that we started the last part with. So instead of a square root, it's a cube root. And I'm going to write that as a 1/3 power. So this is the ln of 2x raised to the 1/3 power minus the ln of 4. Then I can pop down the 1/3. So I'm going to come over here, give myself a little more space to write. This is 1/3 times the ln of 2x minus the ln of 4. And just like the 4 wasn't in the cube root to start, his natural log term out here shouldn't have a 1/3. But both of the 2 and the x are under the cube root. And since there's multiplication going on inside this log, I can come back to this rule and expand him a little further. So the ln of 2 times x is the ln of 2 plus the ln of x. Parentheses here, everybody gets that 1/3 because both the 2 and the x were under the cube root. Close that parentheses because the 4 was not under the cube root, and we get this. And then if you're feeling patient, you can distribute. And that's the fully expanded form there. Any questions on how we did part B? Okay. So I think there's one more part to this guy before I move on. And that's expanding the ln of the 4th root of x cubed. Yeah, that's all. Wait. No, there's also a 3 in here. Yeah, times 3. So in the packet, the 3 is written inside the log in front of the root. I just forgot to write it, so I'm putting it there. But as long as he's inside the log and multiplying the root, we're good. So again, I take the addition inside and I rewrite it as, I take the multiplication inside and I rewrite it as addition outside. So this is the ln of the 4th root of x cubed plus the ln of 3. And then I rewrite the root as a power. So that's the ln of x cubed raised to the 1/4 power plus the ln of 3. And then I've got something kind of complicated going on in here, right? I've got a number or a variable x raised to a power of 3, and then that's all raised to the power of 1/4. Before I bring the power down front, like we did in the other guys, I'd like to rewrite this as a single exponent. So this is the ln of x to the 3/4, because x cubed all to the 1/4 is the same as x to the 3 times 1/4, which is 3/4. And then the ln of 3 is still hanging out. So here I'm using the rule that take a number that's already raised to a power and you raise that to another power. It's the same thing as raising that first number to the product of the 2 numbers' power. So I haven't done anything with the log in this step. And then in the next step, I'll take this power, this 3/4 power, and bring it down. So this is 3/4 times the ln of x plus the ln of 3. Questions about any of these steps? Yeah, no problem, of course. So I think the next one, if I'm going in order, was to do one of those things with asymptotes. So I think there's a few families of functions we've talked about that have asymptotes. One of them is exponential functions. But if we want to deal with vertical and horizontal asymptotes, we should probably look at a rational function. So if I wanted to sketch the graph of this thing, I'm going to need to find the domain, and then along with that, I get any vertical asymptotes. Remember, we learned both of these things at the same time by setting the bottom equal to 0. We need to find any intercepts, any y-intercepts, and then we'd also like to find the horizontal asymptote. So to find the domain, remember we set the bottom equal to 0. This function will be happy as long as you never ask it to divide by 0. That's the only kind of shitty thing it can do. The only way to upset this function, the only domain red flag, I think is the language we used, that there is here is there's some variable stuff in the denominator. So that's a red flag. X plus 1 being downstairs tells me, oh, gotta watch out. This thing could try to divide by 0 if you feed it the wrong number. If you feed this function the number that makes the bottom 0, then the output would be undefined, and so that number can't be in the domain. So we set the bottom equal to 0. That tells us what to kick out. And it tells me that the bottom will be 0 if I plug in x equals -1. So -1 is the number I cannot have in my domain. And the nice way to write this is in set builder. It's the set of all numbers x such that x is not equal to -1. But if you really hate the set builder notation, at this point we should be getting comfy with it. But if you really hate it, you can write that as -∞ to -1, unioned with 1 to infinity. And that's it, that's our domain. Vertical asymptote, we get that info also by setting the bottom equal to 0. So he's just the vertical line. And remember, you always give this as the equation of the line. Vertical line, x equals -1. X-intercepts come from setting the top to 0. So that's 2x minus 6 equals 0, which means you add 6 to both sides, you get 2x equals 6, and then divide both sides by 2, you get x equals 3. So my x-intercept is the point 3, 0. My y-intercept, I get this by plugging in x equals 0, and that's true for all functions. Here are of 0. What I get when I plug in x equals 0 is 2 times 0 minus 6 is just -6. Over 0 plus 1 is 1. So the y-intercept here is -6. That is, it's the point 0, -6. And then the horizontal asymptote's the kind of complicated one. You have to compare the degree of the top to the degree of the bottom. So remember that rule, if the degree of the top is bigger than the degree of the bottom, then there's no HA. If the degree of the top is strictly less than the degree of the bottom, then the HA is y equals 0. And if the degrees match, then the HA is the line that you get, it's the horizontal line, y equals, and then it's the ratio of lead coefficients. Okay, so here for my function, the degree of the top is 1, the top is linear, the largest power of x showing up in the numerator is 1, and the largest power of x showing up anywhere in the denominator is 1. So these are both degree 1 polynomials, the top and the bottom. So I'm in this third case here, which tells me that my horizontal asymptote should be the line. It's always y equals, because it's a horizontal line, 2 over 1, because the lead coefficient of the top is 2, and the lead coefficient of the bottom, remember, if you see just an x, it's always 1x, or just the line y equals 2. So that's how we find all the good stuff. And then we use the good stuff to draw the good graph. So any questions on how we found these things? What this procedure is like? Okay. So then, if I want to draw a decent graph of this, I just sketch in the bits of information that I found, sketch those in first, and then try to complete the picture. So I know I've got a vertical asymptote at x equals -1. We always draw those as dotted lines. If you're using like a TI 83, 84, they might draw this in as a solid line. Remember, that's not a part of the graph. My horizontal asymptote is the horizontal line y equals +2. So I'll call this 1, call this 2. Okay. And then I can plot my intercepts. My x-intercept is the point 3, 0. My y-intercept was all the way down at -6. So this isn't perfectly to scale. And here at 0, -6. And then I know my graph, it has this horizontal asymptote, y equals 2, and he has this x-intercept. So the only way he can approach that horizontal asymptote is like this. So I can fill in this shape here. And he dives off down towards -infinity down there. It's this sort of shape. I just don't really have the space to draw it. All right. That goes, maybe if I do it like this. Right, this sort of shape down here. And then up here, there's something similar going on. And if you look at the picture in your graphing calculator, you'll see something like this. I'll pull up the virtual TI 83 so you guys can follow me. Just share the whole screen, we'll be brave. So if we want to see this picture on our calculator, we'd hit y equals, and then type the numerator in parentheses. So it's going to be open parentheses, 2x minus 6, close parentheses. And then we divide by open parentheses, x plus 1. Whoa, shit. Yeah. 1. And depending on our window settings, we may get a reasonable looking picture here. Oh, let's see. Oh, I might have graphed something. Did I graph something wrong? X equals 3? No. It's not supposed to be negative? No. Was the y-intercept positive? No. What do I draw here? 2x minus 6 over x plus 1. Oh, that's disturbing. So this isn't, oh, it's got to be something to do with my window settings. 10, minus 10, 10. Desmos. Sorry, I don't know if this thing is giving me trouble or if I made a mistake. We'll verify. So did we do a miscalculation somewhere here? Maybe 0? No. -6? No. Yeah, this is what it should look like. Yeah, okay, what we drew is fine. I don't know why my virtual TI 83 is fucking up. But you see this graph, close you because you're not working at that. See this graph and you see our graph, right? Our graph. There's the graph as it is in Desmos. So our scales are a little bit wonky. But yeah, this is what it should look like. And everything is as we calculated it. If I zoom in here, it'll look a little more like our picture. You can draw in the vertical asymptote. But remember that that's not actually, sorry, my mouse is missing. It's not actually a part of the graph. You can draw in the horizontal asymptote, but remember that's not actually part of the graph either, right? That's just something that can't click it. Yeah, all right. So that's the function, and those are the asymptotes. And this is the procedure to get the graph. Were there any particular questions about the asymptote stuff that we wanted to discuss? Okay, so I'm going to keep going through in the order that these are requested in the chat. If you do have a question, remember you can hold the space bar like a push to talk button. Rational functions aren't the only functions that have asymptotes. That's an important thing to remember. Logarithms and exponentials also have asymptotes. Like f of x equals c times a to the f of x equals c times a to the x either looks like this, and it might appear to have a vertical asymptote over here, but it doesn't. It just grows really, really fast. But on this side, let's use the chat more. On this side, we do approach this horizontal asymptote of 0. As we walk further and further out, we get closer and closer and closer to the HA y equals 0. And that's a growing exponential. Decaying exponentials also have asymptotes, horizontal ones, that they approach just on one side, but they approach them on the other side. So this guy gets closer and closer to that same HA. Logs. These have graphs that look like this. And they have a vertical asymptote. That's the line x equals 0. So those are, I think, all the functions we've studied in detail that have asymptotes. The power functions that we looked at that had asymptotes are really rational functions, right? Like 1 over x cubed. Those also had vertical and horizontal asymptotes, and you can get them following the same rules that we used to graph our rational function here. Right, so setting the top to 0 will find you horizontal asymptotes. Setting the bottom to 0 will find you setting the bottom to 0 will find you vertical asymptotes. Setting the top to 0 does not find asymptotes. That's x-intercepts. So moving forwards, the next one we wanted to look at was how to solve a system by substitution, I think. So you want to find the ordered pairs that solve the system. This looks like something that came from looks like something that comes from your take-home exam. If it is precisely that problem, of course, I can't do that here. But I can look at something similar. I think this is you guys right. Yeah, so the next problem that was requested is verbatim a problem from exam 4. So I can't do that, but I can do something similar. So let's find the ordered pairs. Solving the system. How about this and this? We're going to look next at this problem, which is very similar to one of the problems in your take-home test. I'm sorry, I can't do that exact problem, but I think if you follow the procedure here, it's a lot like the nonlinear systems we solved in class, and I don't think you'll have a terribly hard time if you watch this carefully doing the other one. So the system is nonlinear because the variable x occurs to the power 2, and we know that linear systems only ever have any of the variables occurring to the power of 1. So since it's nonlinear, I have to solve this using substitution. Because system isn't linear. For a linear system, I would want you to use elimination. So I can pick one of those equations and solve one of the for one of the variables, and then I'm going to take that and plug it into that variable in the other equation. And it really doesn't matter what you do here. If I solve the second equation for y, that's pretty easy. Y equals negative 2x plus 2. That's my first step. And then I substitute, i.e. plug in negative 2x plus 2 for y in the first equation. So this is how substitution always goes, whether you're talking about a linear system or a nonlinear system. And if I take that first equation, everywhere there's a y, I'll write this out really carefully, y minus x squared equals 3. Everywhere there's a y, I'm going to write this instead. So that will be negative 2x plus 2 minus x squared equals 3. Our mic's muted unless we have a question. That's all right. It's all right. Don't stress. But yeah, let's keep those muted unless we need to talk. So the next move from here would be to combine any like terms, pull everything to one side, and try to factor the polynomial. So if I do that, I will get, I'm going to write this in standard order, negative x squared minus 2x, and then I've got this plus 2, and I'll subtract this 3 over, so I'll have minus 1 equals 0. And now I need to factor this. Right? The glory of substituting is that you get an equation with only one variable. So you can go ahead and solve that explicitly now. You can get a number out for x. Here we'll get two numbers because it's a quadratic. I can try factoring this. If I pull out a negative 1 or I divide both sides by negative 1, this becomes x squared plus 2x plus 1. Are we that lucky? I didn't think we were going to be that lucky. We are that lucky. How does this factor? Well, if I multiply a and c, I need two numbers that multiply to 1 and sum to 2. Those both have to be 1. This is x plus 1 times x plus 1 equals 0, which means x is negative 1. So there's really just the one solution here. These graphs touch at just one place. If I wanted to graph, right, so now that I've found substitute, right, and then here we solve explicitly to get a number. And use the hashtag symbol for a number. And then we're going to back substitute to get the y value. So here, if I take x equals negative 1, I can plug this back into either equation, right? Into either original equation. And if I back substitute negative 1 into, well, this guy's easier to work with than the other guy, right? Y plus 2 times negative 1 equals 2. And then 2 times negative 1 is negative 2. So this is y plus minus 2, sorry, equals 2, which means y is 4. So those two graphs only touch each other at one point, and that point is -1, 4. If you look at the two graphs, so our solution is the point, the ordered pair, -1, 4. And graphing them isn't too bad. That first guy is the same as y equals x squared plus 3. So that's like this. Take the graph of y equals x squared and you bump it up by 3. Or if you like, that's already in vertex form. And the point -1, 4 is right up here. And the line y plus 2x equals 2 is this line that hits that graph in just this one point. So that's what the system looks like. If we'd gotten two x values, two solutions for x back at this step when we factored the quadratic, or if we had to use the quadratic formula, whatever, when we got these values out, if there had been two of them, we know there can be two solutions to this equation, right? Because it's quadratic. Then that would mean that the line hit the parabola in 2 points, which is usually what happens if a line hits a parabola. But it happened to be the case that this line just barely kisses that parabola. That's called a tangent line. You'll learn all about that in Calc 1. But that's it. That means the solution to the system, just this one ordered pair. Any questions about that? Yeah, if you get some gnarly numbers there, if you get some numbers that are not integers, I would prefer them in exact form in terms of square roots. If you give me decimals, I'm not going to beat you over the head as long as you have work that leads to the answer, right? If you just have the answer and it's just in decimals, that's not acceptable because I can't see that you did the work. It looks like you just used a calculator or a Desmos or something. But as long as you have work, you can report the answers as decimals or as in terms of square roots, but I would prefer the square roots. So if you wanted to use 1.4 instead of the square root of 2, I won't beat you for it as long as you have work that leads to it. Any other questions about systems, how we solved this system, what's expected of you regarding solutions on the take-home test? Mm-hmm. Yeah, we can look at another system problem. I do think there are some other questions that came before that, Aiden, so I'm going to go back and see. Okay. There were a couple other questions in here. So Dan asked, if you work better by getting all the easier problems out of the way, will it be okay that the problems are written out of order on the paper? That's fine. If you don't work the problems in order, I totally understand. I do the same thing. And my advice would be to run through the test doing the problems that are easiest to you, and then run through the test doing the ones that look a little harder. And then once you've done all of that, run through and start grinding on the hard problems one at a time. So if they're out of order on the paper, that's fine. Just please number them. The easiest way to keep these organized is to not do more than 1 or 2 problems per page, or at least per side. Number them and make sure your work is nice and clear in its organization. Questions 25 and 53 from the review packet look like those are next. And then some old tests. Yeah, reviewing the old tests is always a good idea. Because this test is online, normally we do paper tests, and those are similar to my tests that I write in class. Because we're doing this test online in MML, I think it would be equally wise to review the homework because they will be in the same format, homework and the quizzes. If you want to calculate your grade, go to the Canvas gradebook and input the appropriate amount of points for each thing as a what-if score. So that's why I have the Canvas gradebook. Otherwise, I wouldn't use it at all. We would just use the MML gradebook. But the purpose of having the Canvas gradebook built up is so that you can go in there and estimate your grade overall. If you want to talk to me about that more, we can talk a little bit after the review. So let's move back to solving problems. I think the next one that was requested was 25 and then 53 from that review. So let me pull the review back up. '25 and 53. So 25 says, without a calculator, solve each of these. I'll write them down. All right. Okay, so I'll bring it back to the dot cam. This is the next problem. Okay. So each of these is a logarithm or exponential equation, and the big tool here for exponential equations like this guy and this guy would be to take logs if needed. There are actually other ways to do both of these because they're both base 10 objects on both sides, but we'll walk through it with the logs. And then the other two are logarithm equations. So the trick for those is going to be to exponentiate on both sides. Nivi, if you scroll to the very, very top of the chat, you'll find the review packet there. I pasted the link. You can also just Google search Santa Fe College review for Common Final, or look at the student resources page on the math department website, which you can find through Google. So for part A, take base 10 logs of both sides. Base 10 because the exponential is base 10. My variable is trapped in the exponent of a base 10 exponential function. So to get him down, to undo that exponential, I need to take a logarithm of the same base. And remember, the base 10 logarithm is called the common log. That's the one where we don't write the base at all. So just log. Actually, these logs are both base 10 logs. But if I take base 10 logs on both sides of the first problem there, 10 to the x minus 5 equals 1,000, then he becomes the log of 10 to the x minus 5 equals the log of 1,000. And then it's the left-hand side's simplification that's so important here. The base 10 log of the base 10 exponential of any shit like this. So the base 10 log of 10 to some stuff is always just that stuff. And remember, without anything written here, that's what we mean. That is the base 10 log. You could write a little 10 in here if you want to. But when you type into My Math Lab, or when you look on your calculator, if you see log without anything written, it's like a square root, has the implicit 2. The log without anything has the implicit 10. So the base 10 log of 10 raised to the power of x minus 5 is just x minus 5. And on the right-hand side, I have the base 10 log, I'm not going to write the 10 because nobody does, of 1,000. And if you want to, you can use your calculator to compute the base 10 log of 1,000. It turns out to be a nice number. It is 3. So this is the same as saying x minus 5 equals, I'll write it in log terms first. Why not? Oh, sorry, x minus 5 equals x is this plus 5. There we go. All right, so you can add 5 to both sides, and then you can simplify that logarithm. Normally that logarithm would be a nasty number, but here it's not. It's just 3, which is 8. Okay. The base 10 log of 1,000 is 3 because 1,000 is 10 raised to the third power. And that's the other way to solve this problem. So the logarithm path is the more general path. This will always work for exponential equations, and that's what your instinct should be. But you could also use the 1-to-1 property for precisely the reason I just described from here to here, because 10 is 3 cubed, 1,000 is 10 cubed. So this is 10 to the x minus 5 equals 10 cubed, because 1,000 is 10 cubed. In other words, because I know how to write both sides as nice powers of 10, I can then just set the exponents equal to each other, which is a hell of a lot faster. There's nothing wrong with the log thing. The log thing will work on more problems than this, but both of these exponential equations are examples of exponential equations that can be solved without logarithms. So I wanted to show you both ways. Any questions on either of those approaches? If the right-hand side here was 100, I could do the same thing and write it as 10 cubed. If the right-hand side here was 10,000, I could write it as 10 to the 5. If it was 999, or anything other than a perfect power of 10, I would need to do this. I would need to do the log stuff. So that's problem A, part A. Part B, we have the log equation, log 2x plus 10 equals 2. And to solve a logarithmic equation, an equation where the variable is trapped inside a logarithm, we have to exponentiate. We have to exponentiate using whatever the base of that logarithm is. And remember, this is a base 10 logarithm if nothing is written there. So I'm going to exponentiate base 10. That means I'm going to put both sides in the exponent of 10. So I get 10 raised to the base 10 logarithm of 2x plus 10 equals 10 raised to the 2. Put in the exponent of. And then the magic here is that any number raised to the base, that number logarithm of some stuff, will simplify to just that stuff. The left-hand side is just 2x plus 10 now. We undid the log, and 10 squared, that's 100. So I'm using the definition of the logarithm, that the base a log of a to some shit is just that shit, and a raised to the base a log of some shit is just going to be that shit. All right, that's really the definition of the log. It's the function that undoes the exponential. Here we're using base 10 because the logarithm is a base 10 logarithm. I know that because there isn't anything written in the base, which always implies that there's a base 10 there. So from here I subtract 10, divide by 2. And I get this. Was there a question there? Part C is the other exponential equation. So that is 10 to the 3x minus 1 equals 0.001. I can do this by taking logs. If I take the base 10 log of both sides, I'm not going to write the base. The left-hand side, according to this rule, is just that shit, which is 3x minus 1. And over here, the log of 0.001, I'll just leave as the log of 0.001. If you put that in your calculator, you'll get -3, because 0.001 is 10 to the -3, and that's the other way we would solve this. So this piece, this whole apparatus here is just -3. So this is 3x minus 1 equals -3. So 3x is -4. So x is -4/3. Oh, sorry, no, that's a +1, +1. So when I add this back over, sorry. When I add 1 to both sides, -3 becomes -2. So that's 3x equals -2. So x is -2/3, not 4/3, sorry. The faster way to solve this, kind of akin to what we did above, let's write this as 10 to the 3x minus 1 equals 10 to the -3. And then since those are both base 10 exponentials, you can just set the exponent equal using the one-to-one property. And from here, it's the same problem as this. All right, add 1 to both sides. And you get your -2/3. Either way is totally acceptable. The log path works for more stuff. The one-to-one property is much, much faster, but it only works on some problems. Okay, I think there was one more of these, right? Part D wants us to solve log of 500 minus 25x equals 3. And just like the other log equation, we solve this by exponentiating base 10. Yeah, let's change this. So somebody asked, can we do this with a different base? Let's change this to a 2. All right, just to mess with things. We did parts A through C exactly as they were in the packet. You can compare those answers to the answers in the packet. If you want to solve part D as it was written, do it without the 10, or do it with the 10 there without the 2, and see how it goes. So what would I do differently here? I want us to do this with a different base. I think that's a really good suggestion. How would I solve this logarithm equation? All I did is change the base from 2 to 10. Everything else is still the same. So what's my trick to get variable stuff out of logarithms?
You raise it to the base.
Yeah, I exponentiate using whatever the base of the logarithm here is. So here, I'm going to exponentiate base 2. I know it can be tempting to say raise it 2, but it's actually different. I'm not raising both sides to the power of 2. That would be squaring. So I'm going to exponentiate base 2. So not a huge deal, but just a little vocab thing if you want to intimidate your next math teacher with your awesome math vocabulary. So the left-hand side becomes 2 raised to whatever that shit was, and the right-hand side becomes 2 raised to whatever that shit is. We stuck those things in the exponents of 2. And on the left, for this rule, 2 raised to the base 2 logarithm of some shit is just going to simplify to that shit. So this is 500 minus 25x equals 2 to the 3. That's not a bad number to figure out. That's 2 times 2 times 2. That's 8. So then we'd solve this how we'd solve anything else. Subtract 500. So this will be -508. And then divide both sides by -25. The negatives will cancel.
Huh?
And we get this. So first I exponentiated with the appropriate base to kill the logarithm. So 2 raised to the base 2 logarithm of some shit is just that shit. 2 raised to the 3, that's 8. and then I subtracted 500 from both sides. So I'm just left with negative 25x equals negative 508. And then I divided both sides by negative 25. And the negatives cancel, and I just get 508 over 25. I don't think those simplify. 25 is 5 times 5. 508 is 2 times 254. 254 is 2 less than a power of 2. So yeah, no dice.
Wouldn't that be 492? Negative
Oh.
492?
Good catch. Yeah, thank you. Thank you. My arithmetic is just awful, isn't it? That's why you guys were scoffing. Yeah, sorry. So yeah, let's come back to here. Yeah, this 8 is positive, isn't it? So when I subtract 500, I'll get negative 25x equals negative 492. Thank you. So then x will be negative 492 over negative 25, and those negatives cancel. 492, I don't think is divisible by 5, so this won't simplify either. Sorry about that. Good catch. Okay, so that's the game, right? To solve log equations, you exponentiate, which is to put in the exponent of, and you use the same base as whatever base logarithm your variable is stuck in. And to solve exponential equations, you take logs. So John's asking, what if I had something like 2 raised to the 500 minus 25x equals 3, something like that? Here I would take the base 2 log of both sides. Because I've got my variable trapped in a base 2 exponential function. So that's the base 2 log of 2 to the 500 minus 25x. And over here I'd have the base 2 log of 3. The base 2 log of 2 to some shit is always just that shit. So this would be 500 minus 25x equals the base 2 log of 3. And then from here I would proceed as I would otherwise. The base 2 log of 3 is not a nice number, so I'll just leave it as the base 2 log of 3. If I subtract the 500, oh god damn it, John, I'll get negative 25x equals the base 2 log of 3 minus 500, and then I'll divide by negative 25. If you're looking for something that you can easily put in your calculator, and you have an older calculator that doesn't have a general base log button, instead of taking the base 2 log on both sides, you might consider taking the base 10 or the natural log on both sides. So I think usually when I work these for the purposes of this class, I could also take the ln or I'll take the base 10 log here because that's what we've been playing with a lot. But this would be the end, right? This is your answer. You're done at this step if you're looking for an exact answer. But if you're looking for something that you can readily plug into a calculator, take the ln or the common log of both sides instead of the base 2 log. And then here, I can use my rule that says the power inside the logarithm can come down. So I get 500 minus 25x times the log of 2 equals, and then the right-hand side is still just the log of 3. Divide by the log of 2. And then subtract 500. And then finally divide by the negative 25. So here x would be log 3 over log 2 minus 500 all over negative 25. So different ways of doing the same thing. You'll notice a lot of similarities between the two answers, right? And in fact, if you use your change of base formula to rewrite this base 2 log of 3, you'll get log 3 over log 2, just like this. So the answers are shaped exactly the same, right? It's some weird logarithm, minus 500 over negative 25. Some weird log shit, minus 500 over negative 25. The only difference between the two is the base. And in order to express the base 2 log of 3 in a base 10 logarithm, I would have done this with the change of base formula. You could have also used the ln here, and it would go the exact same way. If you replace log here with ln, you get the same thing. But if you're working by hand, I advise this. If you're looking for a decimal, so read the question and see how it wants the answer. If it wants an exact answer in terms of logarithms, go ahead and do this, save yourself the writing. If it asks for your answer as a decimal, use the common log, that is the one we used here, or the natural log. Okay, so there were some other questions. How many questions are on the test? I think there's about 30 questions on the test. The last version I was shown had 30 questions, but it's being worked on by other people. So I can't guarantee that that's still the case, but in the range of 30. The first are, you've got free response and multiple choice. And you want to make sure that that you devote a reasonable amount of time to both. Don't blow through the multiple choice to get to the free response, and don't rush the free response to spend a lot of time on multiple choice. They're weighted equally, okay? They're weighted equally. So the test is half free response, half multiple choice. They're equally weighted. Make sure you give enough time to all of them. Caleb asks, if you want to see how the final will affect your grade, take all the grades from the MML gradebook and paste that are in there so far and paste them into what if scores in the Canvas gradebook, and then you can add a what if score for your final and start playing around. Say, oh, if I get this on the final, that should do that to my grade. If I get that on the final, that should do this to my grade. I think, what else do we have here? Is MML average grade different from the Canvas average? Yeah, I'm not entering anything in the Canvas gradebook. That's just there for you to play with. So the Canvas gradebook shouldn't have anything entered by me. It should only have things that you guys have entered as what if scores. I just leave those as blank slots so you guys can play around with it. So we wanted to see number 50 from the packet, and then 66, 72, 74, and 86. So let's do 50 first. All right, we still got plenty of time. So we go for 2 hours, so we're only halfway there. And there is a lot of other stuff in the packet, so it's good that we're doing this. They want us to match each of these functions with their graphs. Let's just draw the graph. I can break out my silly virtual TI-83 again. And we can see if it'll draw for me a nicer graph this time. I don't know why it was being so stupid before. Okay, so what we want to do is graph these things. The log of x, I should know what that graph looks like. But if you don't happen to have that graph shape memorized yet, you can hit y equals log of x and graph that thing. Now this viewing window isn't ideal, is it? I can't really tell what's going on. It looks like it might have a y-intercept somewhere around 0, -1, and it's just very, very hard to see. So I should play with my window settings. Let's just zoom in a little bit. So if I change my window settings, instead of running from -10 to 10 everywhere, running -5 to 5 everywhere, I'm zooming in. And okay, there I'm getting a better feel for the shape, right? It's this weird sort of slow growing thing. It looks like it pokes up through the x-axis right around 1. If I zoom in a little bit more, It appears to have a y-intercept here, but it doesn't. You got to be on the lookout for that. Logarithms don't have y-intercepts. There's actually a vertical asymptote here, and it's tough to see on this graph unless you come way in. So let's change this to that. So you see now on the right over here, it's my x min. Oh yeah, too. Let's center. Sorry, I forgot the negative in front of the x min. Right? So this guy doesn't have a y-intercept. If you keep zooming in more and more and more, what you're going to see is that the graph of f of x approaches the y-axis. It gets very, very close, but it never does touch it. And that's that vertical asymptote that we talked about earlier. So he'll get as close as you want to that y-axis, but he never touches it. There's a vertical asymptote, x equals 0. So this is the graph y equals f of x. This x-intercept right here, remember I have my scale on this graph set to 0.5, so each tick mark is 0.5. The log of x is only equal to 0 when its input is 1. And then if we're looking for some other points we could put on this guy, since he's the base 10 logarithm, if you come all the way out to 10 here, he will at that point make it up to 1. And you can build a table if you like. I think everybody knows how to do that, right? Hit second in graph to pull up a table. You see you get an error here at 0, at -1, at -2. So there are no negative numbers or even 0 in the domain of the logarithm. He doesn't start playing around until the inside becomes positive. So the domain is just open interval 0 to infinity. And then some points you've got 1, 0. If you come all the way out here to 10, you'll have 10, 1. The next whole number y value is going to be at 100. But if you're looking for other points you could use, if I feed this guy a 1/10, I'll get -1 out. So that's another point that is on the graph. Okay. And to get any other base logarithm graph from this graph, all you have to do is swap all the 10s for whatever the other base is. So if I wanted a base 2 logarithm, this would be 1/2 -1, this would still be 1, 0, and this would be 2, 1. If you want to get a better feel for the asymptote, Desmos is your friend. If you haven't played with these graphs, do so. Right, you see here that it actually dives all the way down, but never touches, just gets real close to the x-axis, and that's that vertical asymptote. The point I mentioned, 1/10, -1 right here. Oops, sorry, 0.1, -1 right there. And the other points we can see as well. All right. Here's 1, 0, and 10, 1. Okay. And then the other guys are just going to be shifted versions of those. So if we want to look at those from your perspective, I think it's best to just use the graphing calculator, g of x is the log of x minus 1. You're going to learn all about this in pre-calculus, but if you subtract 1 on the inside of a function, that drags the whole graph to the right by 1 unit. That's what that does. So if I type log of x minus 1, that doesn't look like the right minus. Yeah, there we go. Graph him. Same thing, just all move to the right one. This calculator is having a hard time with the vertical asymptote. Same shape. If we play with the window settings, you can see it a little better. I'll just go back to the standard window. I don't know why this virtual TI-83 isn't drawing that vertical asymptote there, but it is there. Again, we can see in Desmos. These points won't be on the graph anymore because it's a new graph. But here's that new graph. And you see the VA there. And then the last one we wanted to look at, h of x, I'll try to tuck him over here. Log of x minus 2 has a VA at 2 and looks same sort of shape. I'm a little out of space. I guess we'll do it like this. Like this. So this is the graph h of x equals. This is 1, 2, 3.
Hey, you're breaking up on us.
Is the video breaking up or the audio? So these are our 3 graphs. Maybe I'm just, and then if they asked us to do anything else with these, we can take a look. I think they just wanted us to match the graph, right? Match, identify the x-intercept. Yep, so we've done that. The x-intercept for the first guy is 1, 0. The x-intercept for the second guy is 2, 0. X-intercept for the third guy is 3, 0. Find the value of x that makes the function equal to 0. Find the x-intercept for the function. So B and C are the same thing. The x-intercept is the point where y is 0. That is where the function is 0. Yep. And so the blue graph there is F, the red graph there is G, and the green graph there is H. Any questions on this one? Okay. So that was 50, right? And then we wanted to go back to 66, 72, and 74. There were some other questions here. Is the MML, yeah, we talked about that. One that doesn't have base 10, we did that. Subtract, yes, my arithmetic sucks. You don't simplify till the end, yeah. Numbers are different. Caleb, yeah, the numbers could be a little bit different in MML. The versions of the test that I've seen have the random number generation restricted to use smaller numbers, so you shouldn't get anything that's too out of hand as far as the weird numbers from MML are concerned. There will be partial credit on the final. That's why I need you to submit to me all of your written work, and I need it immediately after you finish the final. That's the main purpose for that. It also lets me verify that your work is your own, and that's very important for academic integrity. But the main purpose is so that I can give you partial credit. Yeah, we have about half of the problems have some specific partial credit options in the rubric. So we're going to be grading this very, very carefully, just like we would the normal final. There are some multiple step questions, but those will be questions that have partial credit baked into them. So if it's like a 5-part question, you get parts 1 through 3 correct, then you'll get 3 out of 5 points. And then I'll be looking for more detailed stuff in your written work. Yes. Yeah, you got to write your solution for the graphs on test 4, yes. Yeah, so each of those problems, or most of those problems, if I remember right, say graph the system and then solve the system. You got to graph the system, that is draw the picture of the curves or lines or whatever, and then solve the system. And I specify the method you should use, either elimination or substitution for each system. So yeah, on the take-home test on test 4, please do draw the graphs. Even if you're working on your own paper, that's why I recommend printing it if you can. But if you can't, just do the best you can. Draw me the best graph you possibly can. Some graph paper might be useful if you have any of that floating around. If you can't print the test to use the graph paper I kind of provide in there, then just do the best you can by hand. I'll be looking at those, and I will be as generous as I can. I know not being able to print sucks. So 66, 72, and 70 what? Or next? 66, 72, 74, and 86. So 66 is asking us about graphs of power functions. This is good. We haven't played with this in a little while. So graph A and C have y-axis symmetry. Graphs B and D have origin symmetry. We're told that all of these are graphs of power functions. Graph A shaped like this. B, and I'll switch you back to the dot cam here in just a second, is shaped like this. C is shaped like this, and D looks like this. And they tell us each is a function of the form f of x equals k over x to the n. So when we talked about these as power functions, we would say that these are power functions where the power is negative because they have asymptotes. Here they've rewritten that negative power downstairs as a positive power. So they tell us n is greater than or equal to 0 and is integer. But that's the same as k times x to the negative n. Right? Same thing, just written differently. These two have y-axis symmetry. Which for a power function means that the power is even. Right? Same thing here, y-axis symmetry implies that the power n is even. And then both of these at the bottom have origin symmetry. Which implies that the power is odd. So those we can get just from the symmetries. The fact that the power has to be negative or that the variable has to be downstairs follows from the existence of the asymptotes. The only other thing I might want to know is whether k is positive or negative, right? That number k, the coefficient. The trick to remembering this for power functions is that if you've got something in quadrant 1, k is positive. If you don't have something in quadrant 1, k is negative. So here k is positive. Here k is negative. Here k is positive, and here k is negative. Do be sharp with the greater than, less than notation, right? Remember, greater than 0 means positive, less than 0 means negative, and the alligator always eats the bigger thing. So here this says k is bigger than 0, which means k is positive, right? And we knew that because the graph had some stuff in quadrant 1. If your graph doesn't have stuff in quadrant 1, k is negative. If it does have stuff in quadrant 1, k is positive. All these rules only apply to power functions in this way, but for power functions, these rules work great. Okay. Any questions on this? So which functions are symmetric about the y-axis? A and C. Which functions are symmetric about the origin? B and D. Which have an even power? The two with the y-axis symmetry, A and C. Which have an odd power? The two with the origin symmetry, B and D. Which ones have k less than 0 or k negative? Those are the ones that don't have anything in quadrant 1. So that's this guy and this guy. The other two have k greater than 0 or positive. Moving right along. 72. Any questions about this before I go to 72? If I am going to go ahead and go to 72. I don't mind if you drum, but if you could mute the mic, that would be nice. 72 says we've got a function who's describing the height of some object over some time. So h is the height in feet. The object's time since being thrown is t. And we're on Pluto, so gravity works different. So the function is h of t equals negative t plus 20t plus 25. Sorry, negative t squared plus 20t. What did we say? Plus 25? And they want us to do a few things. This is from the packet. Number 72. Find h-axis intercept. And interpret. E. Find the vertex. C. Sketch it. D. Interpret the vertex. And E. What's the relevant domain? So for what values of t does it make sense to say this function describes an object that's been thrown into the air? H-axis intercept is the same as the y-intercept, right? It's just that here, instead of calling the outputs y, I'm calling them h of t because they're heights. So this is h of 0, which is 0 squared plus 20 times 0 plus 25 is 25. And that means that the object was thrown either from a person who is, by a person who is 25 feet tall or off of a 25-foot ledge or something like that, from an initial height, that's how I would say it, of 25, and remember the outputs here have units of feet. To find the vertex, we use that negative b over 2a formula to get the t value. So here negative b over 2a is negative 20 over negative 2 times 2 times negative 1, yeah, just negative 2, which is positive 10. So this is the t value of the vertex. And then to find the h value, the output there, the height, I would plug that in. So h of 10, what I get when I plug in 10 seconds to this thing is negative 10 squared plus 20 times 10 plus 25. 10 squared is 100, so that's negative 100. The negative's on the outside, so it stays negative, right? Plus 20 times 10, 2 times 10, that's 200. And then plus 25 is plus 25. So negative 100 plus 200 is positive 100, plus 25 is 125. This 10 is seconds, remember. And this h value is measuring height in feet. So my vertex is the point 10, 125. Sketching the graph and interpreting the vertex. This is a parabola. I'm going to mark this as 10, and I'm going to mark this up here as 125, so I can start with my vertex. It's a parabola opening down, because this is a quadratic whose lead coefficient is negative, which means it's going to look something like this. All right. I don't know exactly what those x-intercepts are yet because I haven't found them. But this is a good sketch of the graph. And I also know this. I guess my labels, my scale is going to be way off. This is 25. That's where I intersect the h-axis. So really, I guess if I was trying to draw a better graph, there's nothing wrong with this graph. Just to be clear, you give me this graph, I'm going to be like, yeah, full credit. You know what's going on. But if I wanted to draw a graph where the scales made a little bit more sense, I should have marked the 25 before. So here's 125, call this 10, there's my vertex. 125 is 5 times 25, so it's 1/5 of the way up. This should really be so my graph should look like, more like this. Parabola should be a little bit steeper. That's all. All right, something like that. The same sort of deal. Here's the vertex. It's at 10, 125. If I want to find the relevant domain, it's because I'm talking about an object that was thrown at time t equals 0, and then t seconds later, its height is given by this function. I'm not actually interested in any of this stuff. This stuff doesn't correspond to the real world problem. And similarly, after this object lands on the ground, unless it's, I don't know, made out of like plutonium quarks or some shit, it's not going to burrow into the earth. So I'm really not interested in any of this stuff, and I'm really not interested in any of this stuff as far as the model is concerned, as far as like the shape of the parts of the domain that are related to this problem. So if I want to interpret the vertex, I would say, well, the object is thrown at time t equals 0, and it goes up, 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 until it reaches a maximum height 10 seconds later, and that maximum height is 125 feet. So the object reaches its max height of 125 feet 10 seconds after it is thrown. Right, remember the 10 there is the t value, it's a time. And the 125 is an h value, it's a height. So that's how you keep those two straight. And then the relevant domain would come from finding the x-intercepts. right? Because after this time right here, I'm no longer interested in the graph. So my relevant domain is going to be from 0 up to what this is. So I set h of t equal to 0. I get negative t squared plus 20t plus 25 equals 0. Got to just factor it. Can I come up with two numbers that multiply to negative 25 and add up to 20? 25 is 5 squared, so no way to do that. So it's quadratic formula time. T equals negative b, which is negative 20, plus or minus the square root of b squared, 20 squared, minus 4 times a is negative 1 times c is 25, all over 2a. So that looks like this. And I'll start simplifying that. That's negative 20. 20 squared is 400. And then the two minuses here are going to make this positive. So we'll have plus 4 times 25 is plus 100. All over negative 2. So that's negative 20 plus and minus the square root of 500 all over negative 2. And then I can feed that to my calculator and ask for decimals if I want them. I think for this problem we do want them, so let's go ahead and do that. Move this over here. So I'm going to take negative 20. Turn it on. Get out of this. Negative 20 plus the square root of 500. And then I want to take this whole thing and divide it by 2. So I'm going to hit enter and then divide by 2. Can I move this control bar so it's not in the way? If I type divide here, it will automatically take that previous answer and divide it by 2. So on the one hand, divide by negative 2, sorry. So it's going to be the 1t value, which is coming from negative 20 plus root 500 over negative 2 is, as a decimal, about negative 1.1803. And then the other one is t equals negative 20 minus the square root of 500 all over negative 2. So I'll take my negative 20 minus the square root of 500. Oh shit, what's wrong with that? Negative 20 minus, I didn't, oh, that's right. I keep typing the shift 0 to try and close the square root and it's not working, but there we go. And then I divide this by negative 2. And I get 21.18. 1803 if I'm rounding to the same decimal place. Now, one of these x-intercepts is relevant to this problem and one of them isn't, right? The negative x-intercept, the negative 1.8 here, or 1.18, that's this guy. And I don't really care about him because he's before time t equals 0, so he doesn't have anything to do with the physical problem. But this guy I do care about. 1803. He tells me that my object hits the ground after about 21 seconds. So the relevant domain is the closed interval from 0 to 21.1803. if I round to that third decimal place or fourth decimal place. Questions on this one? The exam is not the same time as class. So please, 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 please look at the announcements, look at the syllabus. It's very important you follow the instructions exactly as they are. The test is 10:30 to 12:30. You're gonna go to Canvas, click on Honor Lock on the left, then click Launch next to Final Exam, and that will bring you into the Honor Lock dialog. You will not be needing tokens, all right? So we haven't talked about this yet. It's a brand new thing. But you will not need tokens for this. The college bought an institutional license for Honor Lock. So after you launch in Canvas, it should just go straight to the like show your ID, scan the room shit. And then if after you do all that, they will enter the exam password for you. You will go to MML, they will enter the exam password for you. And you will take the test in MML. So it's gonna run exactly the same way that we did exam 3. Only difference is they won't ask you for a token. A best calculator is a matter of preference. I've been using an 83 since I was in middle school, so I'm a little partial to the 83, but the 84 is a little bit more capable. It has more RAM, but be aware that there's some differences in how they work. So you need to use parentheses very, very careful on the 83. The 84 will do things like put you up into the exponent and keep you there until you ask to come back out, that sort of thing. I think the exam has about 30 questions. That's my understanding, but it could have grown a little bit since it was last shown to me in a committee meeting. I think we have a little bit more time. This was what, 72, 74? So let's here, 74 was next. We can take a look at this. And then 86. So 74 says, use the discriminant to predict the number of intercepts, horizontal intercepts for each function. So remember the discriminant for ax squared plus bx plus c is b squared minus 4ac. It's the piece under the square root, and usually we call it d. In the quadratic formula. And if it is positive, then this function has two real roots, aka x-intercepts or horizontal intercepts. If d is equal to 0, then there's one real root, aka x-intercept. And if d is negative, then there are no real roots. No x-intercept. But there are two complex conjugate roots. So then for this problem, they ask us to calculate the discriminant for a bunch of different guys and tell them how many roots and of what type. The horizontal intercept on the last one is 21.1803 comma 0, not 0 comma 21.1803. If you put the 0 first, that's a y-intercept. The standards here are going to be about the same as the last one. Not exam 4, not the take-home exam, so the same as exam 3, the standards in MML. You need to know the properties of logarithms, and you need to know the exponential formulas from section 5.3. Those are not going to be provided for you within the test. You have to just know them. So you need to know the definition of the log. You need to know those three properties that allow us to expand and contract logarithm statements. And you should be ready to build any exponential models that you need. Oh, I see. I'm sorry. Yeah, if I wrote them in that order, I goofed up. So the vertex was at 10, 125. Oh, this isn't a point. Yeah, this is the relevant domain. The 0, 21.1803 with the brackets there, this is the domain. So this isn't a point, this is an interval. It's the closed interval from 0 to 21.1803. But the point there, the x-intercept is 21.1803, comma 0. That's the point that we're talking about on the graph. And it tells us that the relevant domain is this interval of t values. Cool, cool. All right, so let's return to 74. They ask us to predict the number and types of roots and then find them. All right. So 2x squared plus 3x minus 5 has discriminant d equals b squared minus 4ac. That's 3 squared minus 4 times 2 times negative 5. Which is 9 minus 4 times 2 times 5. So the minus minus is going to make plus. 2 times 5 is 10 times 4 is 40. This is positive 49. So there will be 2 real roots because 49 is greater than 0. In other words, 2 x-intercepts. This can be factored. This 2 times negative 5 is negative 10. So I can factor this as, let's see, it's going to be 2x squared plus 5x minus 2x minus 5, right? Yep, and so that is 2x times x plus, oh, what is this? No, I can't bring out the 2. Yeah, I can just bring out the x. So that's x times 2x plus 5 minus 1 times 2x plus 5. So finally, this factors as x minus 1 times 2x plus 5. So the x-intercepts are the 2 points, 1 comma 0 and negative 5 halves comma 0, setting each of those factors equal to 0. And for parts B, C, D, we're going to do the same thing. I might not do all of these. I'm feeling a little lazy. For part B, we'd rewrite this in standard form as negative x squared plus 8x minus 16. And then you can calculate the discriminant the same way. B squared minus 4ac here would be 64 minus 4 times, so I'll do it. D equals 8 squared minus 4 times negative 1 times negative 16, which is 0. That's 64 minus 64. So there's just going to be one real root here, and I can find it by factoring. So that's x plus 4 quantity squared with a negative out front. Yeah, if you factor this, you'll get negative x minus 4. Let's do it. So I bring the negative out. So the discriminant is 0, therefore there's one real root. And if I set f of x equal to 0 in part B, Then I get negative x squared plus 8x minus 16 equals 0. Divide everything, or factor out a negative 1. Let's start there and say that is x squared minus 8x plus 16 equals 0. And that's negative, yeah, x minus 4 all squared equals 0. So x equals 4 is my x-intercept. In other words, if you want to write it as a point, that's 4 comma 0. And we know there's only the one of them. That doesn't come as a surprise.
Wait, but
Say that again?
isn't the question like asking for horizontal asymptotes?
No asymptotes, horizontal intercepts. So those are x-intercepts, right? The x-axis is the horizontal axis. They're saying to use the quadratic formula. These first two, you don't need the quadratic formula. You can factor. This one, you will need the quadratic formula. These two, I can't tell at a glance. E, you will need it. C, you will need it. D, you will also need it, yeah. But yeah, horizontal intercepts what they want, x-intercepts.
Oh, okay.
Let's do part D also. That one looks a little tricky, and then we are going to get to take a quick glance at one more. So first I have to write this in standard form, which means I need to square that out. That's x squared minus 2x plus 1 plus 1. So I'm foiling the x minus 1 squared. And then I distribute the 2. So that's 2x squared minus 4x plus 2 plus 1, which is 2x squared minus 4x plus 3. And so the discriminant here, b squared minus 4ac, that's negative 4 squared minus 4 times 2 times 3 is 16 minus 2 times 3 is 6 minus 4 times 4 is 24. So here, the discriminant d is a negative number, right? This is negative 8. So there are no x-intercepts, but 2 complex roots. And finding those with the quadratic formula can be a little bit of work. I know we haven't done that in a while, so let's go ahead and do it. X equals negative b. B is negative 4, so that's 4 plus and minus the square root of b squared minus 4ac. Well, that's the discriminant. I just calculated that, so that's the square root of negative 8 all over 2a. A is 2, so that's a 4 down here. Remember that square root of negative 8 is the same as I times the square root of positive 8. So the negative inside the square root pops out an I. And if I wanted to write these as nicely as possible, I would say that's 4 plus I times the square root of 8 over 4 for one of them, and x equals 4 minus I times the square root of 8 over 4. Both of these can be simplified. 4 over 4 is 1, so that's 1 plus I times the square root of 8 over 4. And this guy is 4 over 4 again is 1 minus I times the square root of 8 over 4. So splitting up the fractions in that last step. The square root of 8 is 2 times the square root of 2, so you could actually cancel a little bit if you simplify the square root of 8 some more. But I wouldn't stress about it. I would be okay with this. If you're curious, root 8 is the same as root 4 times 2. So that's 2 root 2. So I could write this as 2 root 2 over 4 and then cancel the 2. So it's root 2 over 2. That's an option. But I would accept this as it is. All right, we got 5 more minutes. What's going on, guys? What are we thinking? Anything we're really itching to see? Number 76 was requested. Determine, this is good, the number of turning points. So in that first graph, in graph A, there are 2 turning points. One right here, where the graph goes from increasing to decreasing, and one right here, where the graph goes from decreasing to increasing. So this point here where we turn around, and this point here where we turn around, those are turning points. So A has 2 turning points. Graph B has 1, 2, 3 turning points, and graph C has 1, 2, 3, 4 turning points. The number of x-intercepts, this guy touches the x-axis twice, once here and once here. I got someone who wants a cameo. Oh, that's the Nova Kitty. He's a weirdo. He's very cute. So graph A has 2 x-intercepts, one right here by the -5 and one over here. Graph B has 1, 2 x-intercepts, right? Both of them are over here on the left. Graph C has 1, 2, 3, 4, 5 x-intercepts altogether. The leading term in graph A has to be negative. Remember the end behavior dance for polynomials? So because he goes up on the left and down on the right, he has to have a negative lead coefficient. And he also has to be an odd degree polynomial. We'll get to that in part D. Graph B is down on the left and down on the right, which means he has to have a negative lead coefficient and also be an even degree. Graph C goes down on the left and up on the right, so he must have a positive lead coefficient, and his degree has to be odd. Now, part D asks us what is the minimum degree for each of these. So this is, we take what we just said about the degrees and bring it into the picture. We said graph A, because the end behavior is up on one side and down on the other, has to be an odd degree polynomial. And so the smallest possible degree here, it can't be degree 1, because a degree 1 polynomial is a linear function, and that can only have 1 x-intercept. He has 2 x-intercepts. So the next smallest odd number is 3. Has to be an odd degree, we know that, and he's got 2 x-intercepts, so his degree has to be 2 or higher. And it turns out, yeah, this is the graph of a degree 3 polynomial. Graph B, when we looked at that, we said because the end behavior is the same on both sides, either up on both sides or down on both sides, that has to be an even degree polynomial. We said the coefficient has to be negative because it's down on both sides, but now they want the degree. So what's the degree? Well, it has to be negative, and degree has to be even because we're down on both sides, and I've got 1, 2 x-intercepts. So we might think that this has degree 2, pointing down on both sides, even 2 x-intercepts. Okay, well, so the degree has to be at least 2. But you've also got these extra turning points, right? So a degree 2 polynomial is always a parabola. It can't turn around again. So these extra 2 turning points tell me that this has to be a polynomial of degree at least 4. Has to be even, and has to be larger than 2. So the minimum possible degree here is 4 because of those extra turning points. Finally, we get to graph C. Graph C has 1, 2, 3, 4, 5 x-intercepts, so his degree has to be at least 5. And then we asked, does that work with the end behavior also? Yeah, well, the end behavior tells me that the degree has to be odd because we're going up on one side, down on the other. So is it possible that this is a degree 5 polynomial? I don't know. Does it have any extra turning points? I've got 1, 2, 3, 4 turning points, 5 x-intercepts, and the degree has to be odd. So yeah, 5 works here. This could be a degree 5 polynomial. Graph B is a degree 4 polynomial, and here 2 of the roots are complex numbers. That's why you're not seeing 4 x-intercepts. And graph A is a degree 3 polynomial, and one of these guys is a special root right here where we bounce off the x-axis. That's like a double root. So this is coming from a squared factor, and this is coming from a linear factor. So graph A is degree 3, graph B is degree 4, graph C is degree 5. And I think that's about all we have time for. I also think we've answered all the questions in the chat. Yeah, 83 or 84, it's up to you. Some people like the 84. I would say whatever you've been using more through the semester. I think there's 30 questions on the final, but that could have changed since the last time I saw it. There are half multiple choice and half free response questions, and they are weighted equally. So half of the grade will come from the free response and half of the grade will come from the multiple choice. You do need to memorize the equations. You got to know those formulas from 5.3, got to know the log properties from 5.4 and 5.5. Make sure you go back and look at the old shit too. Make sure you remember, like we did, finding the horizontal and vertical asymptotes. Make sure you know the vertex formula, or the vertex form of a quadratic, and the quadratic formula. Those are classics. Those are always going to show up. And I think that should do it. So tomorrow at 10:30 a.m. the test is going to open. That's very sweet. Thank you guys. At 10:30 the test will open. You're going to get there by going to Canvas first. Go to Canvas, click on Honor Lock, go down to the exam. It'll say Final Exam. It might not be there right before 10:30. I set it to pop at 10:30. So go there right at 10:30. You'll see it in Honor Lock. Click Launch. You will not be asked for a token. No more tokens. So just go ahead, launch that thing. Make sure you're ready. You're welcome to have all the scratch paper you want, but you're gonna have to show them that it is clean. So just hold up both sides of any scratch paper. I recommend 3 or 4 sheets. Your pen, calculator, and yeah, that's it. If you do run into any trouble, message me on Canvas, please. It automatically sorts like by section and course code, so I can see what's coming from where and get back to you fast. But you shouldn't run into any problems. Please remember to write your work, remember to scan it, and upload the scans of your written work into Canvas immediately after you finish. If there's like 10 minutes in between where you're figuring it out and getting the scans in, that's okay. If there's like an hour in between, then we're gonna have to have a talk or something so we can figure out what the hell's going on and make sure everything's kosher. And if you have any testing accommodations, I have baked all of those in. Yeah. So anybody who is nervous about that, if you were previously registered with the DRC, or even if you weren't registered with the DRC, but you and I had a conversation about testing times and testing environments, do me a favor, send me a Canvas message just to double check. But I do think I got all of those set up for everybody who needs or requests them through the DRC or anything like that. All right, I am gonna go ahead and stop the video here. I wish you guys a lot of luck tomorrow. I'm sure you can all do well. Please get some good rest, come into it with a clear head, work hard, and yeah, good luck. The grades, oh, don't forget to submit the take-home test tomorrow also, right? That's important. Go ahead and submit anytime before 11:59 p.m. tomorrow, submit the scans of the take-home. All right, have a good evening, guys.